Okay, welcome back everyone. In this segment, we are going to continue our study of periodic motion, but we're going to take a moment to look at some graphs and to see how position and velocity and acceleration are all related to each other and contain information about the amplitude, period, and frequency of periodic motion. So here's a typical graph of displacement versus time. And remember that we said that x is equal to a cosine omega t. Now we're going to add in a phase angle phi at the end of this. And what this phase angle will do is it will start this graph from different points. So in essence, if we add a phase angle, it'll shift our graph. And that's probably the most epic sine function I'll ever draw. Okay. So we want to look at how changing the mass, the amplitude, or the spring constant changes the graph of x versus t. Now as we increase the mass, we're going to be widening out this curve. And if you think about it, this is because omega is equal to the square root of k over m. So as m increases, omega will decrease. And as the frequency decreases, the width of that sine curve gets bigger. Increasing the spring constant has the opposite effect. So again, it's still k over m. So now as k goes up, omega will go up. And as omega goes up, then that means there will be more frequency and the sine wave will become narrower. Okay? Finally, if we increase the amplitude, that has no effect on the frequency or the period. It's just going to make the graph taller. More amplitude means more displacement. Okay. So now we'll look at displacement and velocity and acceleration. And first of all, here is the effect of the phase angle. And essentially what the phase angle does is it shifts the graph, and positive phase angles shift the graph to the left by the amount specified. Okay, so pi over 2 is actually going to be a quarter of the period, because if you think about it, 2 pi is 4 times pi over 2. Okay, when the phase angle is pi over 3, displacement will be this graph here with pi over 3 for phi, and then velocity and acceleration will follow. Okay. Now, how do we get v of t and a of t from x of t? Well, we talked a little bit about this previously. X of t is a cosine omega t plus phi. So if we want v of t, that's just going to be the derivative of x of t with respect to time. And that's negative, usually we write it as negative omega a sine, I can't write today, of omega t plus phi. Now one characteristic of this equation is omega a right here. And we say that omega a is actually the maximum velocity that you can have. Okay, now how is that possibly a maximum velocity? Well, if you think about units, you have radians per second times meters, which is meters per second. And as a matter of fact, we have v is equal to omega r. R and a are playing similar roles. Then we have a of t, which is dv of t dt, which, as we've said before, is d squared x dt squared. Okay, so that's going to be negative omega squared a back to cosine of omega t plus phi. So the argument of the sine or cosine function doesn't get changed by taking the derivative. And, right here, this omega squared a is also the maximum acceleration. Remember that a is equal to alpha times r. Okay? But the other thing to keep in mind is that let's see, how can we say this? A is also, let's see here, omega squared times r, okay? And, oh, sorry, actually that's not what I meant to say. But what happens is that it's kind of a similar thing. So you get radians squared per second squared times meters. That's going to turn into meters per second squared. So this is the maximum acceleration, is omega squared a. Okay, so let's look at this, okay? And actually, here's kind of a cool thing to go back to. Let's go back to our calculation in the gravity unit of the force of gravity inside the Earth, where the force of gravity is negative g mm r over r cubed. Believe it or not, this equation is actually simple harmonic motion of the form F is equal to kx, where x is this r right here, and everything else is k, except the negative sign. All right? So knowing this, how long would it take for someone to fall through the Earth and then return to their starting point? Well, if we think that omega is root k over m, okay, let's check this out, and t is 2 pi over omega, then what we'll get is that t is 2 pi times root m over k. Now let's plug that in here, and we're going to have m, and then k is going to be g, mass of the Earth, mass of the object, over r cubed, which will come up here. Okay? And this is going to give us t is equal to 2 pi square root of r e cubed over g, mass of the Earth. And you can plug the numbers into this, g and the radius and the mass of the Earth, and come up with a time of about 5,070 seconds. Now, what is so weird about this? It turns out that the time to fall down and then to fall back, to fall all the way down and then all the way back, is the exact same times it takes to orbit the Earth at the surface. Isn't that crazy? Well, it's not crazy, because if I square this equation, I get t squared is equal to 4 pi squared r cubed over gm. And you will recognize that as Kepler's third law. R cubed over t squared is gm over 4 pi squared. So the crazy thing is that it's actually the same. So that's a really cool example that I like to show. Okay. Let's look at now how the acceleration and the velocity vary during one cycle of simple harmonic motion. Okay? And you can notice a couple of things. First of all, when we have maximum amplitude, we have minimum velocity. When we have minimum acceleration, we have maximum velocity, and so on and so forth. Okay? So V and A are out of phase by 90 degrees. How do we know this? Well, V of t is a sine function, and A of t is a cosine function. And those are 90 degrees out of phase with each other. Okay? So when V is a maximum, A is 0. And this is the same thing. Okay? And when V is 0, A is a maximum. So there's an inverse relationship going on here. Okay, so we're going to take the same glider as our previous example, and we're going to give it an initial displacement and an initial velocity. And we want to calculate the period, amplitude, and phase angle of this thing. Now, what else do we need to know that we didn't have before? Well, we had omega was equal to root k over m, which was equal to 20. Okay? And we had a mass of this glider of 0.5 kilograms. Okay. Now in order to do this, we're going to have to actually solve both of these parts, A and B, simultaneously. So let's write an equation, for example, for x of t. Okay, x of t is equal to A cosine of omega t plus phi. And we know that when t is equal to 0, we have this value for x naught. So we have 0.015 is equal to A, which we don't know, times omega, which is 20, times t, which is 0. Whoops, I forgot something. I need to take a cosine. A cosine of 20 times 0 plus phi. Okay, so that means that 0.015 is A cosine phi. So that's one equation that we can solve. Okay, we know that the velocity as a function of time is negative omega A sine omega t plus phi. And we know that when t is equal to 0, the initial velocity, v naught, is plus 0.40 meters per second. Okay, now we know the period, by the way. Okay, period is actually going to be omega over 2 pi. Well, how does that work? So omega is 2 pi f, right? And f is 1 over t. So that means that t is 2 pi over omega. And we found that earlier as 0.32 or 0.31 seconds. Okay, so we just need to get amplitude and phase angle, and we're going to have one equation here that has them both. And when we plug in velocity, we'll get a second. So 0.40 is equal to negative omega times A times the sine of omega times t plus phi. Okay, so 0.40 is equal to negative 20 A sine phi. Okay, so now we have two equations and two unknowns, and we can solve this by noting, by the way, this will go into this to make it 0.02. So we have A cosine phi and A sine phi, so that means that the tangent of phi is going to be, put the negative sign over here, negative 0.02 over 0.015. Okay? And that means, believe it or not, negative 4/3. Okay? Now this means that we're going to have an angle of phi of 53 degrees, but typically we'll just multiply that by pi over 180 to get radians that we can plug into our equation. Once we have that, then we can plug that into either of these equations to solve for the amplitude A. So we won't worry about that too much right now. So that wraps up this segment, and next time we're going to be looking at energy in simple harmonic motion.